There is a man hidden inside human DNA. Not his face, not his name, just a genetic trail. Scientists call him Y-Chromosomal Adam, but there is a problem. One study placed him around 338,000 years ago. Another placed him around 138,000 years ago. That is a gap of almost 200,000 years for the same ancestor, using the same kind of evidence, human DNA. So how can one man have two very different ages? To understand that, we need to follow one chromosome backward, the Y chromosome. Most boys receive a Y chromosome from their father. That Y chromosome came from their grandfather, and before him from another father. The pattern can continue for thousands of generations. Think of it like a relay race. Each father carries the same baton. Then he passes it to his son. That son may pass it forward again. But not every family line continues forever. Some men never have children, some have daughters but no sons. Their family continues, but their Y chromosome does not. That particular Y line stops there. Other Y lines continue for a few more generations. Then they stop too. But some lines keep moving forward, father to son, then father to son again, generation after generation, until they reach men living today. Scientists can compare those Y chromosomes. Some look very similar, others contain more differences. Those differences work like small genetic footprints. Scientists follow those footprints backward. The farther back they go, the more branches begin to meet. Eventually, every living Y line reaches one shared point. At that point was one ancient man. Scientists call him Y-Chromosomal Adam, but the name can be misleading. He was not the first man on Earth. He was not the only man alive at the time. Imagine a large prehistoric community. Many men lived there. Many of them had children. Many had their own family lines. But over time, most of their Y lines stopped. One line kept going. That line still connects living men today. That is why scientists study him. Not because he was the first man, but because his Y line survived. Scientists can also follow human ancestry through mothers. They use a different part of our DNA. It is called mitochondrial DNA. When that line is followed backward, it reaches another shared ancestor. Scientists call her mitochondrial Eve, but Adam and Eve were not necessarily a couple. They may never have met. They may not even have lived at the same time. They are simply names for two different genetic trails. One follows fathers, the other follows mothers. DNA carries clues, but it does not carry dates. Scientists must estimate them. In 2013, one team studied a rare Y line. It was called a 00. Their estimate was shocking, about 338,000 years. Another team studied 69 men. They came from 9 populations. That team got a very different answer, about 138,000 years. The gap was nearly 200,000 years. Both teams studied human Y chromosomes, but they used different DNA samples. They also used different calculations. That changed the shape of the family tree, and it changed Adam's estimated age. The biggest difference came from one question: how fast does DNA change? To answer that, scientists use a genetic clock. Imagine 2 old clocks. Both are still ticking, but one runs faster, the other runs slower. Both clocks can still look normal, but they do not measure time at the same speed. A faster clock reaches the same point sooner. That produces a younger estimate. A slower clock takes longer. That produces an older estimate. Genetic calculations work in a similar way. Scientists estimate how quickly mutations appear. One study may use a faster mutation rate. Another may use a slower mutation rate. Even a small difference can move the final age. Scientists may also use different generation lengths. One calculation may use shorter generations. Another may use longer generations. That changes how many generations fit into the same period, and it shifts the final answer again. The people included in the study matter too. A common Y line may show only recent branches. A rare Y chromosome can reveal a much older branch. A larger sample may reveal branches that were previously invisible. Each new branch changes the shape of the family tree. Changing the tree can move its oldest point. That is why the two studies disagreed. They did not simply count the same evidence incorrectly. They built different trees, they used different samples, and they set their genetic clocks differently. Later, other researchers re-examined the older estimate. They proposed an age closer to 208,000 years. That placed the answer between the two earlier estimates. But even that did not settle the argument. The original researchers questioned parts of the new calculation, so the mystery remained. How fast does the genetic clock really tick? Scientists still debate the exact rate. New samples can change the tree. New methods can change the clock. And one rare branch can move the oldest point again. So maybe no one was simply wrong. Each team read the evidence differently. This does not make science weak. It shows science correcting itself. Y-Chromosomal Adam is not one permanent date. He is the best estimate from the evidence available. The next discovery may move him again. Which matters more?